So our next talk is going to be by Tiancheng Xie. He's a PhD student at UC Berkeley, also advised by Don Song. And he will be telling us about Ligero++, a new optimized sublinear IOP. So take it away, Tiancheng.
Yeah, thanks for the introduction. And I'm Tiancheng Xie from UC Berkeley at Don's group. And this is a joint work with guys from Buffalo University and Texas A&M and UC Berkeley. So I'm going to introduce Ligero++. It's an upgrade version of Ligero. So before we go into details, I will briefly introduce the definition of zero-knowledge proofs. A zero-knowledge proof allows a prover to convince the verifier about the validity of some statement, such as a circuit. Such statement can be as simple as a one comparison gate, and it can also be a complex computer program like smart contracts and other styles. And there are three major properties of the zero-knowledge proofs. One is completeness, which means that if both parties act honestly, then the ZKP protocol should also accept. And soundness means if prover is act maliciously, then the verifier should only accept with a small, very small probability. And zero knowledge means the prover holds some secret, and the verifier should not learn the secret during this proving process. So why is this so important, especially in the blockchain? Okay, because it has some very interesting applications, such as Zcash. It verifies that it uses zero-knowledge proofs to verify transactions. A simple example is just verify if my money is larger than a given price. If this, the transaction will be excluded, and it will preserve the preserve my amount of money as a secret. And it's currently deployed in the Zcash called Libra, and I will talk about it later. Another thing is some privacy-preserving applications, such as we introduced before. That's DECO. It enables decentralized identity, and it uses ZKP as a building block to prove the provenance of data, and then we can enable privacy-preserving smart contract. So during the whole blockchain execution, the miner cannot learn the value of smart contract. It can only verify it. So there are many works on the zero-knowledge proof in previous decade, in this decade. So mostly they focus on these four criteria: the approval time, verification time, proof size, and whether there is a trusted setup. So the approval time is defined to be the time consumption of the prover to generate the proof. And verification time is simply defined to be the time consumption of the verifier. And proof size is the size of the communication between prover and verifier. So Libra is widely deployed in Zcash. However, it has some drawbacks. It has very slow prover time, high memory consumption, and it needs a trusted setup for every statement. So in order to solve this problem, these issues, we proposed Virgo and Libra before, and some other team proposed some other protocols. However, like Virgo and Libra only works for a restricted type of circuit called layered circuit, and it needs other protocols as a building block to help it finish the proof. And in Ligero part, the proof size is super large compared to other guys. And we expect them to be like log square or even constant. So in Ligero++, we focus on improving the proof length of the Ligero. And here is a new result. The proof length can be further reduced to polylog by exploiting the structure of the Ligero. So our contribution is reduce the proof size of Ligero, and concretely we implement the Ligero++, and compared to the current open source implementation, we have a concretely faster proof actually, even though we do some extra work. And we also implement Ligero separately and serves as a baseline of the comparison. And we also plug in the Ligero++ as a black box for Libra and Virgo, and we compare it in our paper. So next step can be very confusing, and I will talk about technical details. So prior to the technical details, we have to introduce the format of the statement. It's called RNCS. So RNCS has an extended witness, which is the values in the circuit, the wire value in the circuit, and it introduce constraints to serve as a gate. For example, here is how a multiplication gate forms. First, the left constraint takes just filter the wire in the left, and the right constraint filter the wire in the right, and this is the output wire. And these three wires should satisfy the quadratic constraint x times y equal to z. This is a multiplication gate. And similarly, we can do addition gate, and we can extend even more to custom gate or custom constraints. And this type of RNCS is used everywhere, basically Aurora, Ligero, proofs. I think LibStark use it. So the high-level idea of Ligero is it parses the extended witness circuit as a matrix, and then for each row, it uses read-Solomon code to encode it and commit to the Merkle tree. Finalize it as a read-only matrix using a Merkle tree. So now, before every test, we need to test the whole encode process is correct. So we need to test this larger code word matrix to be a correct matrix. So first, it will take every row of the matrix. The prover will then random linear combination of the matrix of rows and send the combination back to the prover. Sorry, back to the verifier. So the size of the combination is just the row size of the matrix. And prover checks the random linear combination is also read-Solomon code. And then verifier picks a subset of positions and check whether the position is correctly from the random linear combination. So the check 2 will take a column, right? So the check 1 will take a row, check 2 will take a column. So the total communication is size of a row plus the size of column, where in the matrix, the minimal communication complexity can only be square root of n because you take a row and at the same time you take a column. Then after this, we can ensure that the matrix is encoded by read-Solomon code correctly. And now we want to test a linear constraint, A times W equal to 0. And equal to 0 is equivalent to equal to x because we can somehow modify a to satisfy our constraint. So in this case, verify picks a random linear combination. It transforms a times w equal to 0 to r times a times w equal to 0. It's quite of equivalent. Then it becomes two vectors that inner product each other. And notice that the Reed-Solomon code also satisfies multiplicative. So it can multiply we can multiply two Reed-Solomon code together to get a combined Reed-Solomon code. So we combine the Reed-Solomon code, then we do the check that the testing before here, interleaved test, and we figure out whether the resulting code is also valid code. Then we are essentially done with the linear constraint. But this can be confusing, and I will not prove the correctness of this process. This is how the Ligero do. And the proof size is row plus column, which is square root of n. So in order to reduce square root to polylog, we need to exploit the structure of this style of checking. So before that, I will introduce the inner product argument here. It's used in Virgo and it actually construct from the Aurora. It enables the prover and the prover to prove inner product statement. So it runs in a log n time and it only incurs a polylog proof size. It's very small proof size actually. So look, in the linear test, we have check 1, which can be formulated as inner product here. And check 2, luckily we can also formulate a check 2 as an inner product. So the first inner product has size of the row, the second inner product has size of the column. So if we plug inner product argument into this scheme, intuitively we can do a polylog proof size, right? So there is a problem here, since the Ligero will sample multiple rows to ensure the sumness. And it will actually, the Aurora the inner product argument costs more prover time. The constant of the inner product argument costs more. So the intuition why Ligero++ is fast, because the rate of the Ligero is much lower than, the rate of Aurora is much lower than Ligero. So even if Aurora is slower and because we just sample a small set of the matrix, we can, the input to the Aurora is much smaller than the input to Ligero. So a slow Aurora can be tolerated here. And actually, here is an experimental result. The yellow line is Ligero implemented by us. The blue line is Ligero++. And we are actually slower than Ligero because we do extra work in the inner product. But the proof size is much better than Ligero. Actually, it's 40 times smaller than Ligero. And our prover time is just 2 times slower than Ligero. And it's actually faster than current open source implementation in Imperial state. So it looks like the protocol just sits in the middle. It does not outperforms. It's not a rank 1 protocol. And why is this so important? Because it can combine with Libra and Virgo. So in Libra and Virgo paper, there is a polynomial commitment part and there is an inner product proof, interactive proof part. And the contribution of Libra is reduce in interactive proof part to be linear, and it's no longer bottleneck. The bottleneck is a polynomial commitment now. So instead of doing traditional polynomial commitment, we can use Ligero polynomial commitment, and it will speed up the protocol by 3 or 2 times. So that's essentially all of my talk, and there are several future directions to improve it. Can we get even smaller proof size, such as constant size? Because several hundred bytes cannot be used in Zcash, right? And the prover time is still a log n. Can we get a linear time prover? Also, it's interesting to see a distributed prover, because the whole structure can be parallels it easily. So that's all. Thanks for your listening, and I'm happy to take questions.
Great, thanks so much. Well, I'll start off with a question, as always, and give people a chance to post something or raise their hand. So you mentioned trying to get a smaller proof size, and then you mentioned maybe even having it be constant. I mean, do you really think that's realistic? Like, essentially, if you get to a constant proof size, then it feels like we're turning a Stark into a Snark, if that makes sense. So is that something you view as realistic, or is the hope just to get the proof size sort of down?
Yeah, I just hope to get the proof size sort of down, and constant can be super hard to achieve, but currently we are log squared. We can expect like log, and concretely we can expect like several tens of kilobytes, right?
Right. So I mean, I guess the motivation was sort of doing zero knowledge proofs on the blockchain.
Yes.
I'm just wondering if there's really, like if this really seems, I mean, I guess Monero is doing a sort of form of Starks, right?
Mm-hmm.
But in what use cases do you sort of see this being used on a blockchain?
I mean, Ligero ++?
Yeah. Or something, even something with a somewhat smaller proof size.
Yeah, we expect it to use complex smart contract and privacy preserving applications in blockchain. It's not for a small circuit like Zcash, because we can enable a large scale circuit, right?
Mm-hmm. Okay. Do we have any other questions? Bulletproofs aren't a form of Starks, as far as I understand. Well, it depends how you do. So my point is that bulletproofs are not snarks. Verification time is not constant, and proof size is not constant. So hopefully that clears up that question. Someone is raising their hand.
That's me.
Oh, yeah, sorry. Right. Okay.
So I didn't catch what the verification time was, either concretely or asymptotically.
Oh, sorry. So just a moment. So verification time is still slow, because here both verifier and prover has to encode this RT times A matrix, so it's at least linear.
I see. Okay. So are we saying that it's a concrete improvement on, say, bulletproofs?
Sorry.
So bulletproofs also has log n proof size, linear verification, and n log n proving. Can you give a comparison of the constants to bulletproofs? Because it seems like that's the most similar scheme.
Oh, bulletproofs actually here, it's not strictly linear, because they use linear number of cryptographic operations. right? So cryptographic operation can be super expensive, so their constant is super large. And their proof size is actually far better than us. So I have to admit that. For the verification time, I think it's similar. I have no idea for the verification time.
Let me just have a look at the experimental results. Yeah, let's think.
Yeah, so did you, sorry, in terms of the experimental results, did you benchmark the verifier? I mean, you have the proof size and the prover time.
Yeah, we benchmarked the verifier. But the paper is not currently available online.
Okay.
Yeah, I just tried to look it up.
Well, if you could give us a preview of the verifier runtime, that would be great.
Let me see. Just a moment. So, so first I stop the sharing. Let me share another screen. So can you see it?
Mm-hmm. Oh yeah, there's the other.
Yeah, there is a verification time. So it's slightly larger than Ligero still, because verifier has to engage the inner product protocol. And it's similar to Aurora, actually.
Okay. Do we have any other questions? Okay, well, if not, sorry for my background noise. Why don't we, yeah, thank you again, Tiancheng.
Thank you, guys.